Another question that was posed was both somewhat specific and somewhat open-ended. The question that they were asked, I believe in an interview, was to design a memory pool based allocator. And what this person was curious about is what sort of good ways are there to approach this question? And specifically, they were asking about approaching the question of implementing a memory pool allocator. So implementing malloc and free, but using a memory pool as the backing source. But I thought it'd be worthwhile to talk a little bit kind of at a high level, good ways to approach in general any sort of malloc and free question. There's a lot of different ways to ask someone to implement malloc and free, and some of the ways that it's asked don't even always immediately imply, oh, malloc and free. So at a high level, there's a couple of things we need to figure out. For any time you're going to implement malloc and free, whether you're given limitations on it or not. So at the high level, the first thing you need to, or not the first thing, one thing we need to think about is where does the memory come from? Presumably, we're not allowed to use malloc and free ourselves. We're assuming that either malloc and free are off limits or they don't exist on the system. So we can't just call malloc to get memory in order to implement our malloc. So where does the memory come from? And one common approach that many people would use is to do something like sbreak. It frankly doesn't make as much sense in the context of an embedded interview, because sbreak, there's a decent chance, isn't available in that context. But still, it is a reasonable way one could get memory that they could then use to implement malloc and free. And that's how many high-level malloc and frees are implemented. So we could use sbreak. We could do something like a global array. We could literally define an array of bytes at the file scope or some sort of global scope that we would then use subsequently to divvy up, divide up, and use and hand out as part of our malloc and free implementation. Another common place I see it taken from is, well, maybe not taken from, but another common assumption I see made when asked these questions is to say, you know what, I am going to write some sort of a linker script or a build script. And as part of that linker script, I am going to cut out some memory. And at that time, assign a global variable the address of that memory that was cut out. In other words, it might just say, I'm going to define a global variable called heap, and the linker script sets the address and actually allocates some space. So that's kind of a hand-wavy way of saying, well, I need memory. Where am I going to get it from? Well, someone else is going to get it for me. But it's still it's a realistic, real-world approach, and I think a reasonable one that many people would allow you to take. So anyway, and there's obviously other ways we can get memory as well, but these are some of the common ways we need to get memory. So whether we're trying to implement a memory pool or some other system, we need to figure out where we're going to get that memory from. The next thing that we want to figure out is there a known allocation pattern? Oftentimes when you're being asked to implement malloc, it's not simply the question of, well, do you know how to write C code that would implement malloc? it's a question of, do you know how to design good data structures, design a good routine algorithm that works well for the expected use cases. So what is this malloc and free going to be used for? Are people only ever going to allocate and never free? Is it completely random in terms of when things are allocated and freed? Are there cycles? Like, is there a cycle of many allocations followed by many frees? So allocate free. There's lots of different common allocation patterns that you have in a real world system. And in the real world, if you were implementing malloc and free, you would come up with a design that matched the allocation pattern that you expected. So asking the interviewer, what allocation pattern should I expect? And hopefully digging into that a little bit will help you come up with a good design. In many cases, that they might just say, oh, well, it's random allocations, random sizes, random points in time, allocating and freeing. That could be a reasonable answer that the interviewer gives you. If they ask you to implement a memory pool allocator, that strongly implies that there is a particular allocation pattern that they're expecting, because memory pool allocators really only make sense when, well, they don't only make sense, but they have a much stronger argument in their favor when you know the sizes of what's going to be allocated and how many of those things are going to be allocated most likely on your system. And then the final thing we want to think about at a high level, so before we've even written any code, these are all before we've written code sort of aspects, are what trade-offs do we ultimately want to make? Nothing in this world is free. We're always going to give something to get something. Are we concerned about, for instance, how fast malloc or free is? Do we want one or the other of those to be very fast, or do we not care about the speed? Do we want both of them to be fast? Another trade-off is how much bookkeeping overhead are we going to need? Are we going to use a linked list? Are we going to use arrays? What sort of bookkeeping are we going to need? Are we going to keep track of every single byte in this heap with a bitmap, and each byte in the heap is going to be free or in use by setting a bit in that bitmap? Or are we going to take some other approach to the bookkeeping of keeping track of what things are allocated and what things are freed? So that bookkeeping overhead is part of our trade-off. And then the not final trade-off, but I think one other major trade-off is going to be what sort of fragmentation are we going to expect from a particular design, both internal and external fragmentation. And is there a way for us to defragment, or is the fragmentation permanent? We're not defragment, but is there a way for us to fix fragmentation at runtime, or is fragmentation going to be bad once it is bad? So these sorts of trade-offs, and some of these trade-offs might kind of fall more into the once we start writing code, we might start figuring out these trade-offs. Things like, what data structures and data types do we want to use? But keeping track of, like, do we need malloc to always be really fast? And if we need it to be really fast, then we need to choose data structures and approaches to make sure that that ends up being fast. So these are all kind of high level topics. In terms of just a couple mid-level topics as well, we also need to consider predictability versus top speed. Do we want a system that's capable of being really fast, but might sometimes be really slow? Or do we want a system that is always the same speed? It's never going to be great, but it's never going to be horrible. And an embedded system predictability is is potentially more valuable than any of the other things I mentioned. You might be willing to have a slower malloc, slower free, more bookkeeping overhead, as long as it is a predictable and consistent time requirement for malloc and free. And the same thing goes with memory overhead. Is the memory overhead constant, or is it per allocation? In other words, is there more bookkeeping space consumed the more allocations that are made, or are all of the bookkeeping data structures allocated at boot up, and it is hence then a constant overhead throughout the life of that program? So the question once again that was posed was, what is a good way to approach this question? And my suggestion is to, at a design level, start coming up with answers to these questions, or query the interviewer to figure out what sort of design implementation that they would like to see. And sometimes they might throw up their hands and say, do whatever you want, or it's going to be random, or whatever you'd like. And sometimes they might have very specific ideas in mind, or particular objectives in mind that they want you to aim towards. And so that was the question of how to approach this question. The next part is, how would I implement a memory pool allocator? I'm going to get to that in just a second. But with regards to how do we approach a malloc and free question, and once again, a lot of these things aren't specific to malloc and free. There's many other questions where there also are going to be design trade-offs between different elements of it. But with regards to this, any questions about what I've said so far? Okay, so let's move on to the next topic. And I'm rather than trying to write up a bunch of code and you trying to understand my chicken scratch, I had this example that I had done previously, and the code I have up right now was for a slightly different question, but I thought it was a worthwhile example to show, and then we can talk about how this can be improved upon. And first, what is a memory pool? What is a memory pool allocator? Typically, a memory pool is going to be a set of fixed size blocks of memory that are available for use. In other words, we might have 10 blocks of size 100 bytes. The first person who calls alloc gets the first 100-byte block. The next person who calls malloc gets the next 100-byte block, and so on down the line. So we have a pool of memory, and every entry in that pool is the same size. If all of the allocations on your system are the same size, well, then you probably only need one pool. But in most real-world systems, you probably have a handful of different allocations that you're commonly making, and you don't necessarily want to waste a lot of space if your allocations are typically only 10 bytes, or a large number of your allocations are only 10 bytes. You don't necessarily want to waste 90 bytes out of that block every time. So what you would do is you would have one pool that, let's say, is 100 bytes each. And let's actually go the other direction. Let's go bigger. And let's say we have another pool that is 1,000 bytes each. And in both cases, we have 10 blocks of each of these in the two respective pools. And then anytime someone requests to allocate memory that is smaller than 100 bytes, they get one of these. And anytime someone requests something that is larger than 100 bytes and obviously smaller than 1,000 bytes, they get one of these blocks. So what I've done in this implementation is I've defined two global arrays, if you will, where we have a number of allocations. In this case, I think I find it as 20. And then I have one pool that has blocks of size 32 bytes and another pool that has blocks of 128 bytes. So this memory is all allocated and divided up at compile time. And then I also have a Boolean array of the same size that specifies whether a particular entry in that pool is in use or not in use. The implementation of malloc is hopefully fairly self-explanatory here. First, we make sure that the requested size isn't larger than our largest pool, because we can't possibly support it. We return null. And then we iterate over each entry in our pool, checking whether it's, well, first, is it a small size? In which case, check whether or not the Boolean array corresponding to the small heap has that entry free. If not, continue iterating along the loop. Once we've found a free block in that pool, we set it to be in use, and then we simply return the memory address of that block. And if we didn't find anything, then we return null. Implementing free is almost the same thing, other than we don't need a loop. All we need to do is figure out was that block in our small pool or was that block in our large pool? And we need to do a little bit of math to figure out which entry in that pool that pointer corresponds to. And once we find that entry, then we set the corresponding entry in our Boolean array to false. This implementation, hopefully, is relatively simple. There's obviously a little bit of math to figure out whether something was in one pool or another, a little bit of math to figure out what entry it was. So there's a little bit of math involved here and things to do wrong, but both for free and for malloc, hopefully the implementation of both of these is relatively straightforward and simple. I said that this was an example of a memory pool allocator. I didn't necessarily say it was a good memory pool allocator. So I want to talk about a couple ways that this implementation and design is suboptimal. But before I talk about that, are there any questions about what it is I've done here in terms of the code or the design? And by the way, I'm pretty sure this code works. I tested it, but I wouldn't put it past myself to have a small bug or two here or there as well. Okay, so let me point out at least some of the things that jump out to me as being either bad or at the very least inefficient about this design. Oh, so, and before I get to that, let me make one more comment. Here I've defined a pool that has blocks of size 32 bytes and a pool that has blocks of size 128 bytes. And I've also, of course, chosen a number of blocks of size 20. Those numbers should be very consciously and intentionally chosen. Like what one could do is have a general purpose malloc for a system, run your application, run your feature, and log at the end all the different allocation sizes and how many you had of each. You could write some code that did that. And then when you decided you wanted to instead implement a memory pool allocator, you would choose block sizes that corresponded to the allocations that your system was making. So these aren't random numbers. These should be numbers that are very specific to your application. And similarly, I only had small and large. You obviously could have instead had 10 different pools of varying sizes, and you would choose the best fitting pool for each allocation. Okay, so back to what do I think is bad about this implementation? And one thing that catches my eye first is a Boolean array. There's nothing inherently wrong with a Boolean array, other than many systems are going to have each entry in this array be 8 bits, even though we only need logically 1 bit to specify if it's used or free. So rather than having this be a Boolean array, what might be better is for it to instead be a bitmap of some kind, such that each bit in that bitmap corresponds to a particular entry in our pool. So that's kind of one thing that jumps out to me as being suboptimal about this. Another thing that jumps out as less than ideal is the fact that we have this for loop here. There's nothing inherently wrong with having a for loop as part of malloc. But the problem here is that we are allocating over every entry in our pool, even though many of the entries in our pool are likely already in use. So we're going to waste a lot of time every single time we call malloc just rechecking the same things, whether they happen to be in use. So if we truly had a bitmap, what we could potentially do instead is check either 32 or 64 bits worth, 32 or 64 blocks worth at one time. Like rather than checking just a single entry in our pool, we could instead check, okay, are any of the 32 in a 32-bit system, are any of these 32 blocks available? So we could potentially speed it up a little bit and still have the same for loop. Or maybe even better, we could switch this to instead being a linked list. So rather than having these arrays specifying what's free and what is in use, what if we instead had a linked list where everything on that linked list was an available block? So if we had something like so if we had some sort of global head pointer, and then for our malloc implementation could instead be just say return, well, it's not quite that. We would do block return value equals head equals head next return RV. So if we instead had a linked list, and in that linked list contained if that linked list contained all of the free blocks that were available at this time, our malloc implementation could literally be that simple. Just take the first thing off the list and return it. So that would make our malloc a lot faster, but now we have both the overhead of making something a linked list and the overhead of whatever this data structure happens to be. This block data structure, now we need to have something else to keep track of as well. So this is where that kind of trade-off comes into play between faster code or more bookkeeping space required. But in any case, having this for loop here, in my mind, is somewhat of a red flag, and that is almost certainly going to be inefficient. The one upside here is that this malloc being so expensive with this for loop means our free function ends up being very fast and cheap. There's no for loop here in our free code. We can just immediately, in a couple lines of code, free up that allocation. So here's kind of an example of a trade-off between malloc being fast and free being fast. We made malloc slow, and somewhat because of that, free now is quite fast. Let's see, was there anything else I wanted to point out as being bad with this? One other thing that, well, it's not necessarily bad, it just is what it is. Here I only had small and large as the two heap sizes. So I essentially had just copy and pasted code for the small case and the large case. This is probably a bad practice in general, but also probably bad in the context of an interview to have a bunch of copy and pasted code like this. What may have been better is to have essentially well, in here a for loop, and check if this way, for loop for each pool, and then if pointer in pool do something. So rather than duplicating the code, instead iterate over all of your various pools, check whether it's in that pool, and then have a single block that actually handles that code, handles that operation of freeing it. So whenever I see whatever is effectively copy and pasted code in an interview context, like, oh, well, like, why didn't in real life I wouldn't want to see this code, and hence I also would not want to see it in the context of an interview. I want them to show me that they are capable of writing kind of production, not production quality code, but at least production ready code on the first attempt, when there isn't any good reason to do it like this from the get-go. So that was a decent amount of my ramblings about why I thought this was good or bad. But any questions about this kind of design, implementations, concerns about it, or other reasons why it might be good or bad? And I guess just to clarify, I actually like asking the malloc question, and I ask it fairly regularly in my interviews. And I always conclude the interview, or at least conclude the topic of the question with, tell me why your implementation design is good or bad. Like I want them to tell me, regardless of whether the implementation actually is good or bad, I want you to tell me what is good or bad about it. One of the beautiful things about malloc and implementing and designing malloc is that I can always come up with some sort of pathological case that breaks, or at least makes your system really slow or bad in some way. And I can also come up with some allocation pattern that makes it really good. So it's always possible to come up with good and bad scenarios. And if you've finished writing your malloc and free, you should be prepared to answer the question of what about it is good and bad, or where is it efficient or where is it inefficient? And if I wanted to make it more efficient in a particular area, how might I go about doing that? And that kind of post-mortem, if you will, Q&A, in my mind, is almost as important as implementing and being capable of implementing malloc in the first place. Because in my mind, most people can implement malloc in some way, shape, or form. They might do it really bad, like I have here, or not bad, really inefficiently as I have here, but most people can implement malloc and free, at least most people that we're interviewing, that I'm interviewing. But what not everyone can potentially do is tell me what's good and bad about their design, both being able to communicate what's good and bad and being able to know what it is that's good and bad, or efficient and inefficient about that design. Okay, I don't see any other questions, so I'm going to move. Oh, yes.
Now, why only makes sense if we have the fixed block size of memory or memory pools?
Sorry, why does it only make sense?
Just to have the fixed size of memory, like in this case, you have 32 or 128.
Sure. So the question, well, I guess maybe taking a slight step back. The question that was submitted was, how can we implement a memory pool allocator or an allocator that uses memory pools? This is a common way of implementing memory pools. It's not the only way, but it might be the most common way, both in the context of an interview and in the context of real life, to implement a memory pool system. It is possible, and there's not necessarily anything wrong about it, to implement memory pools that are created on the fly. For instance, we could have started off, rather than having this sort of system, instead just had a heap that was some arbitrary number of bytes. And what we could decide to do is at runtime, make allocations of these fixed sizes from that heap. And then once we've made that allocation, then we add it to some sort of linked list that is specific to small and large in this case, and they stay that size for the rest of the life of that program. So in essence, it is a memory pool whose count happens to be determined at runtime rather than being allocated in advance. So that is another way of implementing memory pools, and has the benefit of being slightly more flexible. Like if you don't know what this count is going to be at compile time, it can be more flexible to do it at runtime. The downside of doing it at runtime, well, and once again, the downside of doing it at runtime is you now have a bunch of extra metadata, extra bookkeeping to keep track of which entries are of this size and which entries are of some other size. So upsides and downsides, but that is a potential approach. One thing I didn't really talk about is, well, why are memory pools, why is a memory pool allocator worthwhile to use from the get-go? And I think if it's not obvious, there's two very good reasons why memory pool allocators are popular. One is there is very little bookkeeping required for them. Like in this case, there is, let's assume I used the bitmap, there is only one bit of bookkeeping for each allocation. And that's incredibly tiny. Most any other system that you would look at to implement malloc in free, you're at least looking at 8, 12, 20 bytes per allocation for the bookkeeping and metadata. But in this system, we have almost no overhead for that allocation, which is amazing. It's potentially saving a lot of space. I've worked on systems where we needed to be able to store tens of thousands of really small things, like things that were like 10 or 20 bytes each. And we couldn't waste 10 or 20 bytes for each one of those allocations to manage the bookkeeping. So using something like a bitmap and using this system, we were able to drastically shrink that overhead. So that's one reason why memory pools are so popular. The other reason why memory pools are popular is that they eliminate fragmentation. A major concern with any other sort of implementation or design of malloc is that as you allocate and free things over the life of your program, you end up with places, kind of gaps, if you will, in your overall heap that are too small to be useful to anyone, or at least too small to be useful on average. So you might have a heap that is only 50% occupied. In other words, only half of the bytes in your heap are actually in use, but the remaining 50% of the bytes are so spread out that you can't succeed with any subsequent allocation. That's obviously a bad pathological case, but that is one of the downsides. One of the big concerns that you need to address, or at least consider when implementing malloc in the general case, is what does the fragmentation story look like? And in a memory poor allocator, you have no external fragmentation. Kind of by definition, there is no fragmentation between one allocation and the next. You obviously have internal fragmentation. Within any one block, there might be space that is not being used, but you at least have no wasted space between blocks.